All right, so let's move on. Still mean value theorem. We discussed what is rho theorem, and right now let's look at what is mean value theorem. Okay, and basically, again, let's look at the graph here. If we have a function f(x), which is like this, as you can see that right now fa does not equal fb, right? That is one of the conditions in Rho theorem. Um, and the main idea of the mean value theorem is said that if you have a function continuous on the closed interval from a to b and is differentiable inside this interval, and there gonna exist a point c such that the slope of the tangent line at that point equals the slope of the secant line, which passes through AFA, BFB. Okay, so that's the main idea. That's the main idea. Okay, so I think I missed this here. So just FB minus A over B minus A. Okay, so let's look at the formal definition. The formal mean value theorem. Again, fx is continuous on this closed interval a to b, differentiable. Inside the interval, then there exists at least one point c in AB such that, like I said, the derivative of its tangent line, the slope of its tangent line equals the slope of the secant line passes through those two endpoints. Okay, and you can see from here, right? So, okay, this is the point here is A, f of A. The point here is B, f of B, right? So the slope of this tangent line, which is denoted as f prime of C, right? So as you can see, those two lines are parallel, so the slope are the same. Slope of the secant line is the difference of y over the difference of the x coordinate, fb minus fa over b minus a. And the slope of the tangent line at point C, which is f prime of C, based on the definition of the derivative, right? So that's how we do it. We claim that the Rho theorem is a special case of the mean value theorem, and we can verify that very easily. If you let fa equals fb, do you agree that the numerator on the right hand side becomes 0? So that gives us f prime of c equals 0, which agrees the Rho theorem. Okay. So after that, now let's look at two corollary from the mean value theorem. Okay, and you can actually think about this. First corollary says like this: if the derivative of a given function is 0 for all the x inside this interval, okay, from a to b, open interval here, and then it can guarantee that fx must be a constant function inside of this interval, okay, inside. So, right, remember at every point the derivative is 0, okay, is 0. And then, okay. And also keep in mind it is continuous and differentiable, so it must be a constant. Okay. Second, corollary 2. If we have two functions, fx, gx, again continuous closed interval, differentiable inside on the open interval, and meanwhile, if f prime equals g prime, the derivatives are the same for all the x on the open interval. And then there exists a constant c such that fx, this is not derivative, okay guys, this is a common. Fx equals gx plus c for all the x belongs to the open interval from A to B. And to explain the second corollary, a graph might be helpful. So look at this graph. I have two functions, fx, g of x, and you'll agree that what I did is basically either lift the gx up to some units, right? Or push fx or drag fx down to gx. In other words, there is just a lift. Okay, so difference between those two, and clearly you can see that those two curves are actually identical, right? But it's just that there is some units up or down based on which part to start. And you can see the derivative of those two are exactly the same, but there are some difference between them. So maybe we'll call the difference is c. Okay. So if you, based on gx, if you up c units, you're gonna have f of x. Okay, so that's basically what we call the second corollary from the mean value theorem. Okay, so now it's a little bit theoretical here, and let's trying to use the mean value theorem. Maybe we should do a little bit of proof. Okay. All right, so let's try to do this. Okay, guys. Remember that in the property of the log